All right, we're back. We're going to just pick up where the other video left off. So we're on this example on page 47 of the notes. Suppose IQ scores are normally distributed, mean of 100, standard deviation of 15. We want to find the probability a single individual has an IQ larger than 115, and also the probability that a group of 36. So there's two separate problems here, and we just learned this formula here. And we're going to use this formula when we have a sample mean. So X bar, we use that formula. But for an individual value, we use our old formula. So problem number 1 says find the probability that an individual, so there's the key word there, has an IQ score greater than 115. So this is a problem that we've done before, or similar problems. Here's the drawing. We find a z-score. This is equal to 1.0. We can go to our normal table and look at 1.0. And that's 0.8413 right there. We know that's the area to the left, so we can just subtract that from 1. So 1 minus 0.8413. And that's equal to, what is that equal to? That's equal to 0.1587. Okay, and you could do this just as easily on the calculator, normal CDF, 115 for your lower bound, a large number for your upper bound, 115, 100 for your mean, and 15 for your standard deviation. Okay, so this problem is just review. We've done problems like this before. All right, and so the next problem is find the probability that a selection of 36 individuals has an IQ greater than 115. So the key here is that this probability is for 36 individuals, and the previous one was just for one individual. So if 36 individuals, we want the probability that the average was greater than 115. That's going to be a much smaller probability, remember, because, well, you might not remember, but it's just less unusual to have one individual with a higher IQ score, but to have an average that is further away from the mean, such as 115, is going to be unusual. So having an individual with a high IQ score isn't that unusual, but having 36 individuals with an average IQ score greater than 115 would be, because some people are going to have lower than the mean, some are higher, so your sample mean wouldn't be too much different than your population mean of 100. Okay, but I can set this problem up the same. My drawing wouldn't be really any different than the one above, so I won't do that. But I want to calculate a z-score, but using that new formula. So I have 115. Now that's the sample mean. That's X bar. And that's why I'm using a different formula. So I'm still subtracting 100, but now I'm going to divide by a sigma, which was 15, divided by the square root of our sample size, which is 36. Okay. And so this is equal to 6.00. And our table doesn't even go that high. Our table only goes to about 3.4. Depending on what table you're using, yours might go a little higher. But by the time you get all the way out here, the area to the left is close to 1. And that means the area to the right is going to be approximately 0. So there's about a 0 chance of getting a sample mean from 36 individuals of 115. Okay, so that's quite a bit difference in the answer there. Remember, there was about a 15 or 16% chance of getting one individual with that high of a IQ score, but to get a whole bunch of individuals an average score is not going to be that high. Very unlikely. And so this next question, if you remember it from the last video we saw, it doesn't matter that it's not normally distributed as long as your sample size is greater than 30. And since ours is, so n is greater than 30, then we can rely on the results of the central limit theorem. Okay, so we can use these methods even if the population isn't normally distributed. All right, let's do the next one. Cans of Coke are labeled to indicate that they contain a 12 ounces. A sample of 36 cans yielded a sample mean of 12.19. So this is our X bar here, our sample mean. Assuming that Coke's cans are filled so that mu is equal to 12, and the population standard deviation is 0.11, find the probability that a sample of 36 cans will have a mean of 12.19 or greater. And I forgot to show you how to do that last one on the calculator. I'll just go ahead and show you how to do this one on the calculator. You can still use the normal CDF function. But we'll do the z-score first. So I take 12.19 minus 12. And then I take 0.11, which is our standard deviation. Because I'm dealing with the sample mean, I have to divide by the sample size, or the square root of the sample size. So our sample size, again, is 36. And we get another very high z-score, which isn't unusual for these types of problems. You just have to remember when your z-score is very large in magnitude, that means the area in the tail is going to be about 0. And so our z-score is about 0. I mean, our probability is about 0. So what this is saying that it's very unlikely to get a sample mean of 12.19 or greater. And so let's go ahead and do this one on the calculator since I forgot to do that last time. We go to the normal CDF just as we did for the other problems from chapter 6. And it's the same idea. We want to put in a lower bound. In this case, our lower bound is 12.9. And then we want the area to the right, so I just put in some large numbers. And then I put in a mean. So our mean was 12. And then I put in a standard deviation. Now our standard deviation is for X bar. And so here's the standard deviation that I have to put in right here, 0.11 divided by the square root of 36. I can just type that in there, divided by the square root of 36. It's just 6, but let's go ahead and just type in 36. Okay, so that's the important thing, is to remember to put in the correct standard deviation. Our standard deviation of X bar is not 0.11. It's 0.11 divided by the square root of 36. Okay, and here I get about the same answer. See, this is a negative 25. That means I would have 24 zeros in front of this 1. And so here, again, I have a very small number, approximately 0. Okay, so these results suggest that on average, it's very unlikely to get a sample mean of 12.19. That doesn't mean that individual cans won't be 12.19 or greater, just on average. So it doesn't really get at that issue of whether an individual can be filled up to that amount. All right, the next section is actually very important for the rest of the class. We are going to be using either sample proportion or sample mean quite often for the remainder of the course. This is very important that we know the difference between the two. So proportion is calculated when you have a categorical variable. So when you have a categorical variable, you summarize it by calculating a percent or proportion. When we do that from a sample, it's denoted with a P and then this caret above it. And so we call that P hat. So that's our sample proportion. That's also an estimate for the population proportion. When we have a sample mean, that usually means we have a quantitative variable. The sample mean is denoted X bar, and that's used to summarize quantitative variables. It's very important the next couple weeks that you recognize the difference between the two. And so here we have a couple examples where we're supposed to state whether it's a proportion or a sample mean. In proportion, remember categorical variables, sample mean for quantitative variables. And so in the survey, a random sample of 2,613 adults were asked whether they had voted. So here's the variable right here. Whether they had voted is yes or no. And so that's a categorical variable. And so we would use p hat. For categorical variables, we use p hat. A researcher was interested in whether or not usually means categorical, and except for here, sorry. The advertised weight of a candy bar is accurate. So here we have weight, that's actually the variable. So the student sampled, hold on one second. Can I call you back? Thanks, bye. Okay, the student sampled 30 bars and the weight of each one was recorded, so that's a quantitative variable, and that's X bar. Next question, 100 customers at a bar were asked whether they smoke cigarettes. That's a yes or no question, so that's categorical, so we would use p hat. Summarize the proportion that had or hadn't smoked a cigarette. And a researcher was asked whether they get enough sleep. She interviewed 200 students and asked them, interested in whether they get enough sleep. She asked students how much sleep they got. This is a quantitative variable. I'm just going to write Q. And so we would summarize that with the sample mean. Okay, so that's about it. This other section just talks about the sampling distribution for sample proportion. Just like the sample mean, we can talk about the distribution of the sample proportion, which means how much the sample proportions would vary if you took multiple samples. And we denote the population proportion with the letter P. As I said above, the sample proportion is denoted with p hat, so with the caret. So it's important to get the notation correct. P is for population proportion. P hat is for sample proportion. And because of the central limit theorem, we can actually calculate a z-score for probability. And if we did that, we would use this formula right here. And we're not going to do that right now, but in the next couple sections we will. Thanks. See you later.